Okay, good morning. So, let us get started. Today we will discuss about resource sharing among real time tasks, because so far we have considered the situation where tasks share no resource, but that was unrealistic. In a real situation, practical situation, tasks will be sharing some resources or other, and we will just discuss about the issues that arise and the difficulties and how these are addressed in the commercial operating systems, real time operating systems. So, let us start with that. So far we considered CPU is the only resource that is shared among tasks, and CPU is a serially reusable resource in the sense that it is used by only one task at a time, just like the other resources we will discuss about memory and devices. A CPU is also used by one task in a uniprocessor system, but the difference is that the tasks can be preempted at any time without affecting the correctness. So, as long as there is only one task is all right, but the tasks need to share many other types of resources other than the CPU. For example, the files, data structures and devices are common resources that are shared, and many of these resources need to be used in a preemptible mode. Actually, the part of the code in which a non-preemptible resource is accessed is called as the critical section in the operating system literature. So, it is the part of the code where once the code is entered, execution starts, it should complete without releasing the resource, right. So, that is the idea of a critical section, even though sometimes we loosely talk of critical section as a resource, but it is actually a piece of code. The traditional operating systems, the typical solution is to use semaphores, but in case of real time tasks, if we try to use semaphores, we will get problems. The problems are known as priority inversion and unbounded priority inversion. Let us understand this problem, because very fundamental problem, very basic thing. Even if you tell somebody that I have done a course on real time systems, they will likely to ask, what do you mean by priority inversion and unbounded priority inversion, possibly the first question, right. So, that way it is very fundamental question. So, first let us understand what is meant by priority inversion. The idea is that when a task is executing its critical section, it should not be preempted from resource uses. I am not saying CPU preemption, I am saying that when a task is executing its critical section, it should not be preempted, because then the resource become inconsistent, right. These things we know from the first course on operating system. But the consequence in a real time application is that if a task cannot be preempted, a lower priority task, then a higher priority task will keep on waiting, and we will have a situation when the real lower priority task is making progress with its computation, and higher priority task is waiting, and this is against the basic assumption we had in the scheduling algorithms, that as long as there is a higher priority task, it should execute, the lower priority task should yield. So, this is the priority inversion occurring, where a lower priority task is executing and the higher priority task is waiting. Now, when a task is executing and has accessed a resource in the exclusive mode, then it can block a higher priority task let us say that this is a lower priority task TL, which has acquired a resource R, and after some time the high priority task was released, and it waits for the resource R and the lower priority task until it completes its execution. The resource will not be available to the higher priority task, it cannot execute, right. That is the main problem. But we will see that priority inversion by itself is not a big problem. A simple priority inversion can be handled, we will see how. But the one that is very difficult to handle is unbounded priority inversion. Let us understand what is meant by unbounded priority inversion. Consider the situation that a low priority task is holding a resource. So, there is a resource and a task was executing. After some time it just acquired the resource, and meanwhile a higher priority task was released and is waiting for the resource, right. This is the simple priority inversion situation. But what if some tasks which do not need the resource, that are of higher priority than T1, but lower priority than T2, also get ready and start executing? Because they do not need the resource, they will preempt, they will not wait for T1, right, they will preempt T1. So, let us say we have a task T3 which does not need the resource and it preempts T1. So, T2 will wait for T3 to complete and then T1 to complete. But the thing is that there may not be just one intermediate priority task, there might be multiple of them, and as a result T2 keeps waiting for all these intermediate priority tasks to complete, so that T1 will finally execute and release the resource and then T2 will proceed, but that may be too late. So, this is just an example of a unbounded priority inversion. Let us say we have 6 tasks and T1 has the highest priority and T6 the lowest priority, and this is the timeline, and we will just show the tasks which is using the CPU. Let us say T6 is the lowest priority task executing at some instant, and then it just locked a resource, a critical resource, and after some time a high priority task has become ready and immediately preempts the lower priority task T6, starts executing, but after some time it needs the resource CR. Whenever it issues a lock CR call, it gets blocked. Now, T6 should execute, but what has happened meanwhile, that other tasks have become ready and we are just waiting. So, T6 does not get the CPU, T5 gets it, executes for some time, and T3 meanwhile is waiting, is executing, T4 is executing, T2 executes for some time, T5 again gets back the CPU, starts executing, and after all this T6 gets to use the CPU and completes resource usage, unlocks the resource, and then only the task T1 can start executing. So, the priority inversion that T1 suffered is from this point up to this point, right. Until this point it was suffering priority inversion and is likely to miss its deadline. So, the number of priority inversions suffered by a high priority task can be too many and is likely to miss deadline whenever unbounded priority inversion situations occur. The high priority tasks are very likely to miss its deadline, and there are many situations where systems have malfunctioned because of the priority inversion problem. The most celebrated example is the Mars Pathfinder. You will find widely documented in the internet and in the book. So, this was sent to the Mars on it landed actually on 4th July 1997, and it bounced onto the Mars surface by airbags, so that it will not get damaged, and then it had a vehicle which will roam around the Mars surface called as the Sojourner. So, the Sojourner rover is the one which was released to roam around the moon surface. The Sojourner actually roamed around, gathered transmitted data, voluminous data, started transmitting to the earth, and there are many pictures that were sent. Many of these pictures are available on the internet, you can easily find them, just a simple Google search will give you. This is one of the picture. See the rover vehicle here, the land rover, the Sojourner rover is on this Pathfinder, it is sitting on the Pathfinder, and this is one of the pictures sent. Just see the surface of the Mars taken by the rover, but unfortunately soon it started experiencing total system resets. Each time the system reset, huge amount of data was lost, and it appeared in all newspapers saying that Mars Pathfinder is getting into problem, and they used many terms. Some said software glitches have occurred in the Mars Pathfinder, it is not taking commands, it is resetting itself, and some papers they said that the computer was trying to do too many things at once and it was crashing. That was other reports, and the Pathfinder actually was using a real time kernel, which we will discuss later as a type of commercial operating system, the VxWorks, which is the vendor is Wind River Systems, who sell this VxWorks real time operating system, and RMA scheduling of the threads was used, and the Pathfinder contained an information bus, basically a communication channel, which was a shared memory to communicate among various tasks that execute on the Pathfinder and the land rover, the rover. Now, once it started resetting itself, one thing that was done is that the VxWorks, it provides a facility to run it in the trace mode. In the trace mode, we will also discuss when we discuss about these operating systems. In the trace mode, the important system events like when context switches occur, when synchronization primitives are used, when interrupts occur, the different events are recorded, and the jet propulsion laboratory engineers, they spent hours trying on a replica of the spacecraft that they had in the lab, and where they had set the trace mode on, and they were trying to replicate the precise conditions under which the reset was occurring. Now, after spending lots of hours there, they came to the following conclusion, that the VxWorks uses a mutex object, which we will call as the technique to handle priority inversions, and it accepts a Boolean parameter indicating whether priority inheritance, we will discuss priority inheritance, whether priority inheritance should be enabled or not. And after spending many hours, it was clear to the JPL engineers that if the priority inheritance is turned on, then this kind of situation would not occur. And the initialization parameters, that is including whether the inheritance is set on or not, priority inheritance is set on or not, these are stored as global variables. And this header part of the C program, where the variable is set on, was uploaded to the spacecraft, and then the system started working. So, this was a celebrated example where the system failed due to unbounded priority inversions occurring. It was debugged, found that yes, because the mutex variable was not initialized and priority inversions, unbounded priority inversions are occurring. Therefore, the system was resetting each time, and once they uploaded the header with the priority inheritance turned on, and from that point onwards the vehicle started working, and for another 6 months or so it worked correctly and sent many pictures until it finally was abandoned. So, let us see, when a simple priority inversion occurs, that is a high priority task is waiting, what can be done? Now, the longest duration for which a simple priority inversion can occur when a high priority task is waiting for a low priority task, it is basically how long the low priority task will use the resource in the exclusive mode, is not it? Simple thing. The maximum duration for which the low priority task will need the critical resource is the duration for which a simple priority inversion will occur. We are not talking of unbounded inversions. Now, if simple priority inversions were to be handled, it is not very difficult. Somehow reduce the maximum duration for which a task will need a critical resource. How can you do that? You limit the time for which a task executes in critical section, maybe by careful programming, or maybe by splitting its access to a critical resource across multiple instants, right. Do part of it, release it, and then acquire it, try to do something for low priority task. Many solutions can be proposed. So, simple priority inversion, if it was the real problem, it will not be really that difficult to handle it, but as I was saying that the tricky problem is the unbounded priority inversion case. Now, let us see how unbounded priority inversion can be handled. So, let us see the situation, a low priority task is holding a resource, a high priority task is waiting. So, low priority task is holding, high priority task is waiting, an intermediate priority task has come in, preempted T1, started executing, and T2 is waiting all through, and there are many instances of those intermediate priority tasks which are keeping on coming in and preventing the high priority task from acquiring the resource, because low priority task is not able to complete its resource uses. I hope that is clear, is not it? So, since this is an important point, and later also somebody would ask you what is unbounded priority inversion, just as a final example, let us see this situation that a low priority task has acquired a resource, high priority task is waiting, and intermediate priority tasks one after other arising and requesting CPU uses, and meanwhile low priority task is not able to complete, the high priority task is waiting all through. So, the high priority task that is waiting for all these unbounded priority inversions is likely to miss its deadline. A simple solution was proposed in the form of a priority inheritance protocol by Shah and Rajkumar. The main idea is that a task in its critical section cannot be preempted from resource uses.
You can roll back the task, you can roll back completely the initial situation.
But how can you see the question, I mean the suggestion is giving there is that we can somehow get back to the situation where the task started using the resource. But how do we do that? Because no, it has used the task and we need to make a copy of that, and then we need to but see, it is not a checkpoint. You have to just take a complete backup of the resource, restore the resource. It is computationally expensive, right, and storage wise expensive.
Still it can miss the deadline.
Yeah, it takes time.
Instead of waiting that much long time, restoring to just previous point is can it tolerate it?
No, let us just understand the situation actually. The situation is that the task needs a resource for few milliseconds, right, maybe microseconds. Now, if we have to keep a trace of what it has been doing, or let us say a checkpoint where the resource is backed up and then restored, then it is not that it has just used that resource, it might have performed other computations based on that resource uses, right, and all those are going to become inconsistent. So, it is not just one critical resource you need to back up, maybe all other changes that it has done to other resources need to back up. It is a tricky problem considering the time constraint of few milliseconds.
Overheads also may be.
Overhead, yeah, time overhead also, the task is going to miss its deadline. If the high priority task is waiting for the resources to be restored, when the constraints are few milliseconds, microseconds, deadlines can be missed. So, let us see what the suggestion or what is the solution they gave. They said that, see, a task of course cannot be preempted, low priority task, once it has acquired a resource, but only thing that can be done is that allow it to complete as early as possible, because a simple priority inversion is not a problem. The problem is that if unbounded priority inversions occur. So, a task in the critical section cannot be preempted, that is for sure. What we can do is allow the task to complete execution without incurring the preemptions by intermediate priority tasks. So, how do we make a task that is holding the resource to complete as quickly as possible? So, the idea is that we can raise its priority so that the low priority task is not able to preempt it, right. So, that is the basic priority inheritance principle. The idea is that, see, the low priority task, because the priority was low, a higher priority task was able to preempt it. Those were the intermediate priority tasks, right. Now, what we can do is raise its priority, but raise by how much?
To that extent, which is demanding the resource, TH process.
One less than the
priority.
one less than the
Equal to the
highest resource that
equal to the
Equal to what?
TH or equal to the highest priority task waiting for the resource.
Okay, yes. Yes, that is exactly, see, what they are saying is that the task should be raised to a priority which is as much as the priority of the task that is waiting for the resource, because if you raise it to anywhere lower than that, then we will have intermediate priority tasks which will preempt it. So, we should not have intermediate priority tasks coming in and preempting it, and that is basically equal to the highest priority task that is waiting for the resource, and in that case there will be no intermediate priority tasks. Yes, exactly, that is the solution that was proposed by them. So, the priority should be raised to as much as that of the task that is blocking it, that is blocked, right. The task that is holding the resource should be, the priority of that should be raised by as much as the task that is waiting for the resource, the highest priority task. Now, when a resource is busy, the requests to lock the resource are queued in FIFO order. See, multiple tasks might come in, wait for the resource, right. We just shown it, just one task has waiting, but it is likely that multiple tasks might be waiting for the resource. Can you visualize the situation? See, maybe a low priority task TL was using the resource R, and meanwhile some other task TI requested the resource, right. TI started executing and then requested it, and it blocked, and then TL was executing again, and then TH, a higher priority task, started executing because that time it did not need resource, and it continued up till the point it started requesting for the resource R, and at that time it blocked, and there will be two tasks waiting for the resource R, right. So, we will have to find the highest priority task that is waiting for the resource, and then we have to raise the priority of the task holding the resource by that much. And as soon as the task releases the resource, it should get back its old priority.
So, but in this case we are assigning it to the maximum priority task.
Yes.
So then why are we using a queue? Why not a heap? Like where the maximum?
No, see, actually the ways we will discuss that point later. See, the question is that why exactly we are saying a FIFO queue. See, many operating systems, for simplicity, they let tasks wait in a queue and then use a round robin scheduling among them. Some of the operating systems, some operating system is just a queue. We'll see, we'll discuss those issues with specific reference to commercial operating systems. Some are just FIFO queue, some are FIFO queue with round robin scheduling, and the number of tasks is not large. Just imagine, just remember that the number of tasks that may be waiting for a resource may be at best 2 or 3 maximum, and heap or something does not make sense there, because anyway just looking up 3 does not take time, right. A heap becomes meaningful, a priority queue, when the number of tasks waiting is large enough. Okay, so let us proceed.
But in situations like this, Mark's Pathfinder and all, that may be the solution, because this may be more complex and more tasks may be.
Okay, see, a more complex system, as you are saying, has many tasks, right, but many tasks waiting for a resource for a small interval of time is bounded. It can be 3, 5, that is all. You can't have many tasks in a millisecond arriving and waiting for the resource, right. So, a queue is a solution that is used in many operating systems. So, let us we will discuss those things later. Now, let us understand the basic ideas here. So, that once the high priority task, once the low priority task has completed its resource uses, then it gets back its old priority. Of course, this is natural to expect, but only thing is that if it is holding some other resource, then it should get inherit the priority of the highest task waiting for that resource. It has released one resource, but it might be holding other resources. So, that we have to consider.
So, if it is holding 2 different resources,
Yes.
then in that case the highest priority task which is waiting on
Of course,
any of
exactly,
these 2 resources.
exactly, of course. So, it should be the highest priority task among all its resources, whose priority should determine the priority of a task. Now, let us look at the priority inheritance protocol, the basic pseudocode, simple one, whatever we discussed just written in pseudocode form. Whenever there is a resource is available and a request is there, granted. So, you do not check the priority, whether it is a low priority, high priority, nothing. As soon as the resource is, as long as the resource is available, it is granted. if the required resource is held by a higher priority task, then wait for the resource, nothing needs to be done, because this is not a priority inversion situation, is not it? Because already a higher priority task is using the resource, and it is natural a low priority task will wait for it. But if the resource is held by a lower priority task, then we will have to apply the inheritance clause here. So, not only the high priority task wait for the resource, but the low priority task has to inherit the highest priority task in the queue. But let us understand how does priority inheritance protocol prevent unbounded inversions.
Task cannot preempt now.
Exactly, because the priority of the task is raised to that of the highest waiting task, there is no intermediate priority tasks which can preempt the task from CPU uses. So, this is just an example of the working of the inheritance priority inheritance protocol. A task Ti with priority phi was using the resource CR, and in the next instance a task with priority 10 started using the CPU, and then this was preempted because Tj did not require the resource, it started executing, but after some time it needed the resource and it started waiting for the resource to be released by Ti, and Ti got execution on the CPU, it started executing on the CPU, and due to the inheritance protocol the priority of Ti is raised to 10 because Tj is 10. So, the inheritance clause, by that the priority is raised, and after it completed the resource uses, its priority was changed to phi, and then Tj has got hold of the resource and it will start executing now. Is that okay? The protocol is very simple, basic priority inheritance scheme, but there are problems with this protocol. Why? This is not used as it is in the operating systems. Two main problems are deadlocks and chain blocking. It is let us see what is chain blocking, and we will see how deadlocks can occur here. Now, first let us look at deadlock. Let us assume that we have two tasks T1 and T2 that are accessing the resource CR1 and CR2, and let us assume that T1 has higher priority than T2 and T2 starts running fast. So, T2 is the lower priority, T1 is the higher priority. T2 locks, let us say, resource R2, it started executing, locked R2, and that time T1 started executing, preempted T2 from CPU uses, locked R1. And then it, after some computation, it tried to lock R2, but R2 is the lock being held by T2 and it will block for T2, right, and T2's priority will be raised to that of T1 through the inheritance clause. But T2 they have already got into a deadlock, right, even if its priority is raised, already got into a deadlock. So, using the simple priority inheritance scheme, deadlocks can occur. The other problem is chain blocking. The definition of chain blocking is that whenever a task needs a set of resources, if each time it needs one resource, it has to wait and undergo priority inversion, then it for a set of 5 resources, it has to separately wait 5 times to get the resource, and we will say that it has undergone chain blocking. Assume that a task T1 needs several resources. So, T1 needs, let us say, CR1 and CR2, simple example, 2 resources. So, after some computation, so it blocked for T2, and then T2 released CR1 after executing for some time, and T1 could execute with CR1, but after some time it needed CR2 and then it started blocking again, right. This is example of a chain blocking. We can also have a situation where multiple tasks are holding different resource and it is waiting for T2 for getting CR1, it is waiting for T3 to get CR3 and so on. So, a chain blocking is the situation where a task to get the set of resources it needs, each time needs to block for one resource.
But in the previous slide, how was chain blocking a problem?
I mean, you are saying that why is chain blocking a problem, is it?
Because T2 is running now, so we have the tasks running in the processor. What's the problem?
No, it is not a deadlock situation, it is the delay that is causing the problem. See, each time it waited for some microseconds to get CR1, then it will wait again to get CR2, to wait again. Just see the problem, the multiplication of the delay for each individual resource. Undesirable situation, this can cause problem, right? Chain blocking can cause problem. Deadlock is definitely unacceptable, but chain blocking also can cause problem if the tasks have tight deadlines.
So this principle, it just converts the unbounded priority inversion to a normal priority inversion.
Exactly. Yeah, see that is a interesting observation. See, we have not eliminated a simple priority inversion. A simple priority inversion can never be eliminated, but what we have said is that a simple priority inversion can be tolerated by careful programming, by splitting the access to a critical resource of a low priority task into small chunks. So, simple priority inversion, we will see all these protocols which are refinement of the basic inheritance scheme and which are used in the commercial operating systems. They cannot eliminate a simple priority inversion, but what they are targeted is to eliminate unbounded priority inversions. Okay, so I hope whatever we discussed so far is clear, right? So, let us just try to answer a few simple questions.
Sir,
Yes. And
when does a process is blocked for some resource,
yes.
and another higher priority process comes and it also blocks for the same resource.
Yes.
So the priority inheritance takes place during the suspended state or when one of the lower priority tasks is executing. At what time does the priority inheritance takes place?
Okay. So, let us the question is that when does the priority inheritance takes place. So, let us see the basic pseudocode we had seen. Let me just get back there, so that this question we can answer. See, this is the pseudocode that we saw here. Whenever there is a request for a resource, this pseudocode is applied. Any task is requesting for a resource. If it is resource is free, no problem, grant it. If the resource is held by a higher priority task, no problem, just keep on waiting for the resource. If it is held by a lower priority task, then it waits for the resource, first thing, and also the priority inheritance clause is applied.
Okay, so in this scenario, the lower priority task is running on the processor.
Yes.
So what if the lower priority task is itself not running and the higher priority task is waiting for a resource which is held by the lower priority task which is not running on the CPU? So in that case, will the lower priority task inherit the priority of the higher priority task?
Of course. See, this clause does not say that which task is running, right? It is saying that if the resource is held by the lower priority task, then apply this. Does not say that whether the lower priority task is running or not, nothing. As soon as there is, sorry?
If this pseudocode is getting executed,
this current process is running.
Need not be. Like he says, the current process may not be running. So, the lowest priority task holding the resource may not be running, it is blocked by another, or maybe the higher priority task was waiting, it was running and then it has requested the resource. So, the lower priority task, like the example that we had shown here, just see that. Where is that example? Yeah, this is the example. See here. See here, the lower priority task was running for some time and then it was preempted by the higher priority task, and while the higher priority task was running, it requested the resource. So, very likely the lower priority task will not be running when the resource is requested.
Actually, this the pseudocode, the scheduler will be executing that pseudocode.
Yes.
At that time, no process will be running right now. At that point,
Okay.
the scheduler will be executing.
No,
that
the
pseudocode.
one that was running before it was requested. So, maybe that was his question. But the thing is that whenever a resource is requested, lower priority task will definitely not be running, because the request is being by some other task, isn't it? Lower priority task will not definitely be running. Yes, please.
So you are saying that a task can hold more than one resource.
Yes.
Then there may be a list of many tasks which are holding on separate resources.
Yes.
So in that case, a task will have multiple priorities or is one single priority.
You mean one task having multiple priority? No, no, no. See, a task will get the highest priority of all the tasks that are waiting for various resources that is being held by it. So, the priority inheritance protocol is simple but has problem, that is why it is not used as it is. Now, let us look at some very simple questions based on the priority, simple priority inheritance protocol. So, let me get back to the point where we just left it. All these we had seen. Yeah. So, priority inversion, if somebody asks you what is priority inversion, what would you say?
Actually, it's the situation where the higher priority task waits for the lower priority task because of a resource held by the lower priority task.
Yeah. So, lower priority task keeps on executing and a higher priority task is waiting. So, that is a priority inversion. Now, just tell me whether this sentence is true or false. See, when several tasks share a set of critical resources, it is possible to avoid priority inversions altogether using a suitable scheme, like he was asking, no, he pointed out. So, no, because that he has already pointed out that a simple priority inversion is very difficult to prevent. Now, when a priority inheritance is used, what is inheritance related inversion?
It is maybe when we when we increase the priority of a lower priority task, some intermediate tasks between the higher and the lower are not being executed on the processor.
Exactly.
So it's like it's like a priority inversion because physically the priority of that lower priority task is lower itself.
Yes. So, what he said is correct. See, he says that, see, we had a low priority task TL and a high priority task is waiting for some resource held by it, and as a result the TL inherits the priority of the high priority task. But there may be other tasks, intermediate tasks, which do not need this resource, but still they cannot proceed with their computation. They are undergoing inversion, they should have completed because they do not need this resource. So, that is a inheritance related inversion. Now, let us look at the next question. When a set of real time tasks share critical resources using the priority inheritance protocol, the highest priority task does not suffer any inversions. False, right? What about lower priority task? When a set of tasks share a certain critical resources using priority inheritance protocol, the lowest priority task does not suffer any inversion. Will it be correct? Yeah, lower priority task cannot, by definition itself, it cannot suffer any inversion. Now, when a priority inheritance scheme is used, a task needing a resource undergoes a priority inversion due to a higher priority task holding the resource, due to a lower priority task holding the resource, due to an equal priority task holding the resource, either a higher or a lower priority task holding the resource. What about you? What is your answer? Which one is the correct option here? Priority inheritance scheme is used and a task undergoes a inversion in this when a higher priority task is holding the resource, a lower priority task is already holding the resource, equal priority task is holding the resource, and either a higher or a lower priority task is holding the resource. Yeah, exactly. When a higher priority task holding the resource, inversion cannot occur, and the equal priority task holding the resource also, inversion does not occur, because it is at least the same priority. And this also, either a higher or lower is not true, because lower priority task, a higher priority task cannot cause an inversion. So, it is only this one, second choice. So, now let us see what are the improvements that were proposed to the basic inheritance scheme to make it more usable, because when deadlocks and chain blocking is there. Okay, I think there is one more question. Using semaphores of traditional operating system, what is the maximum duration for which a task may undergo priority inversion? So, that is we are trying to use the semaphore of the traditional operating systems and we are trying to find out the maximum duration for which a task will undergo inversion. Is it equal to the longest duration for which a higher priority task uses the resource, the longest duration for which a lower priority task uses the resource, some of the durations for which different lower priority tasks may use the shared resource, or greater than the longest duration for which a lower priority task uses the shared resource? So, what about
Because as soon as the lower priority task releases the resource,
yeah.
then what is the case of inversion? Again, it completes.
Okay, so they are thinking the second option is correct, but what about you here?
Unbounded inversion, the third one works.
Sum of durations for which different lower priority tasks may use the shared resource, is it?
Because
The time for which they use the resource. Anybody has any other answers? The answer is actually 4. The answer is that it is greater than the longest duration for which the lower priority task uses a shared resource, because here even when they are not using the resource, they are just holding it. Still there may be intermediate priority tasks which are not requiring the resource, they have preempted it, right. So, only thing we can say is that it is longer than the maximum duration for which a task holds the resource. That is all we can say. We can't say that it is some of the durations for which different tasks need the resource. So, now let us see some of the improvements that were proposed to overcome the problems of the basic priority inheritance scheme. So, we will first look at the highest locker protocol. This is again a solution which is a straight extension of the inheritance protocol, but itself has problem. It solves some of the problems, I mean the main problems that the basic inheritance scheme, it overcomes those, but it creates new problems. Now, we will see the priority ceiling protocol after this. We will see that that is the one which is actually used, the priority ceiling protocol. But to be able to understand the priority ceiling protocol, we need to discuss about the highest locker protocol, because unless we look at the highest locker protocol, ceiling protocol may not make too much sense. So, first let us look at the highest locker protocol. In the highest locker protocol, the idea is that a ceiling priority is assigned to every resource. Look at all the resources, find out who are the tasks using it, and then assign a ceiling priority to the resource, and the ceiling priority is computed as equal to the highest priority of all tasks needing that resource. If we find that 3 tasks are needing that resource, we will set the ceiling priority for that resource as the highest of all the 3 task priorities. We will take some example and also explain. Now, once we have computed the ceiling priority, the rule is simple here. Whenever a task acquires a resource, any task, the rule is straightforward here. Whenever a task acquires a resource, raise its priority to that of the ceiling priority. Simple rule here. So, whenever a task acquires a resource, its priority is raised to the ceiling priority of the resource. It addresses all the shortcomings of the basic inheritance scheme, the priority inheritance scheme, but we will see that introduces new complications which will be addressed by the ceiling protocol. But if we understand the highest locker protocol, then understanding the priority ceiling protocol will be easy, because priority ceiling has many clauses, and straight away understanding it might appear a bit unnatural and difficult. We should understand highest locker protocol, find out its problems, and then understanding why something is done in priority ceiling protocol will be easy. So, here during the design of the system, a ceiling priority is assigned to all critical resources that we had seen, and the ceiling priority is equal to the highest priority of all tasks using that resource. So, if R is the resource, for every resource R, we will find out which are the tasks using the which might use the resource, that assumed to be known, that which task will use which resource, which data structure, which device, etc., be used by one task. And based on that, we know the priorities of these tasks, and we will set the ceiling priority of the resource R is the maximum priority of all the 3 tasks. So, let us stop here. We will continue from this point in the next class. So, any questions, etc., make it, please keep it ready. You can ask during the next class. Okay, fine. Thank you.